Hi everyone, welcome to my YouTube channel of hiking and photography adventures in Aotearoa, New Zealand. It is time for another useless fact. I'm sure you're very excited, and I'm going to build on the theme from last week. This time we're going to look at one of the other numbers that you'll find printed on your lens, and that is aperture. Now, last week's video, I got a bit carried away. It was a bit long. This one's going to be nice and short, I promise. Now, I know what you're thinking. We already covered aperture several times, so why are we covering it again? Well, we've talked about what aperture is. That's the opening in the lens that lets light in, that you can open and close to let in more light or less light. We've also talked about the creative effect of aperture, which is that it alters the depth of field, or how much of your picture is in focus. But what we haven't done is talked about what the actual numbers mean. So if we take a look at a lens like this one, and you were to open up the end of the lens and have a look on the front, you'll see a number, and that number will be 1 to 2.8 in the case of this 12 to 35 lens. And that is your F number, which you will often see referred to just as 2.8. But that 1 to 2.8 is actually critical because aperture is a ratio. And what is that ratio? Well, aperture is a ratio of the focal length of your lens to the physical diameter of the opening. And with some simple math, we can actually calculate how wide physically the opening is. And you do that simply by taking the focal length and dividing by the F number. So we're going to use a calculator, and we're going to use this 12 to 35 lens as an example. Okay, so we take our focal length, which is 12 millimeters, and we divide by that F number, which is 2.8. And we can see from that that the physical opening is 4.2 millimeters across. A little tiny opening. Now, I know what you're thinking. This is a zoom lens, so how does that work at 35 millimeters? Well, we can do the math again. So 35 millimeters divided by 2.8, 12.5 millimeters. So you get a significant enlargement of the aperture hole as your focal length gets longer. Which brings us to a critical point. This is a zoom lens with a constant aperture. That means that the ratio of the diameter of the hole to the focal length stays the same even as the focal length changes. And as we've just seen, that means that as you zoom in from 12 all the way up to 35, your aperture to stay at 2.8 has to physically get wider. That makes for a much more complex lens. It also makes for a much bigger lens. So a lens with a constant aperture will be more expensive and be larger than a lens that doesn't have a constant aperture. Here's another example. This is my Leica 8 to 18 millimeter lens. If we pop the cap off and have a little look on the end, what we see is that we have our ratio, which is our full aperture details, 1 to 2.8 dash 4.0. That's because this lens has not got a constant aperture. So at 8 millimeters, the widest aperture is 2.8, and we can do the math again and we can see what that means. So 8 millimeters divided by 2.8 gives us, drum roll please, 2.8571428571. Pretty small aperture. But at 18 millimeters, the largest the aperture hole will go is f4. So 18 divided by 4 gives us 4.5 millimeters. Now, if we wanted this to have a constant aperture, that would mean that at 18 millimeters, you would need an opening of 6.4 millimeters. So a slightly larger hole. Not significantly, but it does require a bigger and heavier lens, larger glass elements, and so on. Now, there are more extreme cases. You will remember my 100 to 400 millimeter lens, and it's very common in telephoto zoom lenses to have a varying aperture, and you're about to understand exactly why that is. So if we look at this one, it has an aperture of 1 to 4-6.3. So at 100 millimeters it has an aperture of 4, and at 400 millimeters it has an aperture of 6.3. Now, why is that? Well, let's do the math again. 100 divided by 4. At 100 millimeters it has an aperture of 25 millimeters. At 400 millimeters it has an aperture of 63 millimeters, significantly larger. And if we wanted a constant aperture of f4, we would need an aperture at the widest end of 100 millimeters. Now, 100 millimeters is pretty big. It would require this lens to be significantly larger. And that, my dear friends, is why constant aperture, and particularly fast, long lenses, are enormous and very, very expensive. You are welcome. Thank you for watching, and we'll see you next week for another useless and impractical fact.